Welcome back, and in this lesson we're going to be creating a program that will be able to model and reduce a fraction that the user inputs. So our goal here is to make a program using methods that will allow us to say, okay, if the user enters a certain fraction, say it's 6/3, then we should be able to reduce it to its lowest possible form. If it is something like 6/3 or it's 6/6, you want to make it into a whole number, and if it's not, then you want to reduce it to its lowest possible form. So if you had something like, for instance, 20/10, that would be an example of the whole number. Or if you had an example of something like 21/12, then you would have to reduce it down to 7/4. So our goal here is to take a fraction that the user inputs and reduce it down. But instead of using many different types of variables and many different types of methods here, we're going to use one single type of method, and we're going to see if we can overload it. That way we can practice everything we've been talking about so far. To do this, we're going to create a new project, and we're going to call this project methods test. And if we give it its name, remember, the Java projects have no naming conventions on them, so we can give it whatever name we'd like, but we're going to say methods test, and then inside methods test, we're going to make sure we create a new class file. We're going to call this program the fraction reducer, because that's what it does. So again, descriptive class name. Now we can also try to put in our main method, but now we can start to analyze it a little bit more, because remember, we now know what all the keywords mean. We know that the public and the static are modifiers to see who can use it and how can they use it. Void is the return type, because once the main method finishes running, the program is over. And then the name is main, with the parameters of string square brackets args, which, as you'll see later on, means it takes other parameters that you can take from the command line. So let's say we also want to make this program repeat, because we do. This type of program, it's a simple command to the user, so many times they're going to want to do this more than a single time. Therefore, we should support this. Now remember, if we are repeating, then we only have a couple of things outside the do-while loop. One of them has to be the scanner input object being created, and we're going to be taking input from the keyboard, so we provide the parameter of system.in. And in fact, this is another example of a method call, even if you don't notice it because it doesn't have any parameters on it. System.in is just a method. It's a method that says this is where you take input from. So even parameters for a object such as the scanner object can be methods themselves. Then we have to make sure we create our counter variable that tells us, does the user want to continue? We're going to call this the integer user continue. And remember, we have to initialize it, so we'll give it a value of 0 initially. And then we think, do we have anything else that we need to keep constant between program runs? We don't, so we can create our do-while loop. And then we know what the condition is going to be, and we can easily just add that in right now, because that's a very set constant value here. We simply say, while user continue is not equal to -1. And then we have to make sure we ask the user right here, that they should want to continue. So we prompt them right at the end of our program, and we'll simply say, if you want to continue, enter a number other than -1. Again, the implication being that if they enter -1, the program will stop. And then we assign the result to the integer user continue. Now we can start to think about, what do we really need for this program? Now that we've got all the stuff about repetition out of the way, we can start to say, okay, now what does this program actually need? Well, we know that we have to ask the user for the value, and then we know we have to pass it to our to the parameter, or as a parameter to our method. And the way we're going to do that is by asking the user for two numbers. So they say, for example, 6 enter 7, because otherwise we'd have a slash in the middle, and that would make it very difficult to manipulate. So we're going to say, please enter the numerator, then please enter the denominator, and then we return to them the reduced form. So we have two separate print statements, where we have to say system.out.println please enter the numerator. And then we have to do the same thing for the denominator, so we can copy paste that and just change the last word. And then, just as always, we have to assign it to a variable. This time we're going to create the variable right here, and we're going to say the integer numerator is equal to the input that the user just entered, because remember, this is the unmodified reduced form. It's possible that they might give us a reduced fraction, in which case it'll be identical, but what we really want here is to make sure that, hey, we need to take in the numerator and the denominator as the user enters them without changing them in any way. That way, if later on when we were modifying our program, if we needed to manipulate the original entry in some way, for example, if we wanted to add in the ability to multiply fractions, then we would need to be able to use what they gave us right here. So, we now have to think, what can we put into our method? Because we know how to create our method, but remember, to create a method and effectively use it, we need to think of our situation. Our situation here is that the method should be able to reduce a fraction. Now remember, there's a lot of ways to reduce a fraction, and there's no limitation that says we only need one extra method. We could add in as many methods as we like. So we have to think, first of all, how many methods do we need? And then, what will each method do? In this case, since all we need is the method to reduce, or we need to reduce the fraction down, we can use a single method. However, inside this single method, there has to be a lot of breaking down. First, we'd have to be able to check to make sure that it's not going to be the already reduced form. So, we would have a single check that says if it's already reduced, just return it as is. Then, if the fraction isn't already reduced, we have to reduce it down, probably going to be using a while loop, since we don't know how many iterations we have to do, and there's a variety of ways to reduce, and we'll get into that a little bit later on in this own lesson. And then we have to say, okay, if it's not reduced, and we've already reduced it right now, we have to check again to make sure that it's not going to be a whole number, so it's not numerator equals denominator. And then finally, we have to decide, do we even want to return this to the calling method? Or, in this case, since what we're really going to be doing is printing this back out, can we simply say, okay, just return this back out to the user using a print statement, therefore giving the method a void return type. All of these are choices. Some of these choices have bigger impacts than others. Now, that final choice, the return type, that's a big choice to make, and you have to decide at the beginning, because otherwise, you can't be changing your method afterwards. We have a choice of either saying, well, we'll construct a string inside the method that'll say numerator/denominator and return that, or we can simply print it out. Now, as we've talked about before, most of the time you're going to want to return a value, not print it out, because we don't know immediately that what if we don't want to output this to the user? What if later on we're going to be using this program as a means to activate another run, so that another program can pass it a fraction and they can reduce it. So in this case, it doesn't make sense for us to simply reduce, or for us to output the value. We should probably just return it to the calling method. So we now know what we have to put into our method signature. So we're going to say it's public, because we want this to be available to all classes, static, because we're not going to be creating instances of the fraction reducer class, at least not yet. And then it's going to have a return type of string, and remember, string with a capital S, because this is the data type string, and then our name, in this case, reducer. And then we have to decide, do we have parameters? We do. In this case, the parameters are going to be the numerator and denominator. We're going to call this integer n for numerator, and integer d for denominator. Now we're going to be following the convention of having the numerator first and the denominator second. This is a choice, but if it's the generally followed way of doing it. So n is going to stand for numerator, d is for denominator, so they're going to follow in that order. Now we first, as I mentioned, have to make sure that it's not already reduced, because our goal here is to not use system resources when we don't need to. Therefore, we should first check if it needs to be reduced at all. And by checking if it needs to be reduced at all, we can also combine that step into a step of actually reducing. So that way, we can reduce everything. If it doesn't need to be reduced, then no operations will really be done. And then, if after that, the numerator equals the denominator, then we know it's a whole number, and we won't have to check again after we reduce the values. So, to reduce, we're going to use a while loop. This while loop is going to be a while loop because we don't know how many runs we're going to need. Think about it. You might have a number that's very large, and therefore you don't know the first or the best factor for it. Therefore, you could easily say, well, I need to have a run here that'll break everything down, and it'll say, okay, now these are going to be the lowest common, not the lowest value possible. The way we have to do that is by finding the greatest common divisor. Now, if you recall, we actually already did a method called greatest common divisor. We put that in the in the addition repeated class, but if you want, we can actually just copy this over. So, instead of having to call this method separately, we can put all of our methods for this class into this single class. That way, we have a class that uses two methods. But think about it. There's one big change we need to make here. Since the GCD is only relevant to reducing, it's not going to be relevant to other classes. We can simply make this a private class. Now you might be saying, well, what's the advantage of a private class, of a private method? Isn't this a disadvantage because all it does is limit who can use it? Isn't that a problem? Well, there's some methods like this where you don't want other classes to be able to use it. We already have a public form of this, and we want to make sure that this GCD method is going to be specific to reducing fractions. While right now that doesn't seem like a big deal, later on we're going to have programs where there's a separate implementation for one way of doing it and a different implementation for every other type. So in this case, even though they're going to be doing the same thing, we want to make sure that it's private so that only our class can access this GCD method. So we're going to say we can now call our GCD method on these two numbers. That way, we'll be able to get the greatest common divisor, and we can check, okay, we can now say that instead of having to do another run, instead of having to copy this into our method, we can simply call another method and then just use that every time. This is the big advantage of methods. You compartmentalize your tasks so that you don't have to keep retyping the code. Instead, we have it in one location, and whenever we need to call the GCD, we simply call the method. Now, we have to call this method in a very specific way. Remember, this method, when we built it, only worked for if n1 was bigger than n2. So, to make sure our program works, we're going to have to make sure we follow this. So we're going to have a statement right here, an if statement, that will make sure that the numbers are in the right order. A consequence of this, though, is that it might flip the numerator and denominator around. So to change this around and to make sure that we still keep the numerator and denominator as separate variables, but we can flip them, we're going to make sure that we assign the numerator to a new value and the denominator to a new value, at which point we'll switch them, and then we can start to figure out the GCD. So it sounds complicated, but it works better in implementation. To switch, we're going to have an if statement that says if d is greater than n, then we want d to be set to a value. So we're going to say that we're going to have the integer temp, and that's going to be equal to d, or n. It's up to you, because there's no real advantage or disadvantage. You have to switch them either way. We're going to pick n, just because it's the numerator we tell them to work with it first. Then we're going to say that we have to switch the two values around. Now, to switch these two values around, remember, we're going to create two variables right here. We're going to create the integer n1 and the integer n2. This is so that we don't contaminate which one is the numerator and denominator, because 3/5 is not the same as 5/3. So to switch them, we have to make sure we separate out which one's numerator and which one's denominator so that later on we don't get confused. Then we're going to say that the integer n1, which we don't have to redefine, so we'll say n1 is equal to d. And then, because we know that that d was bigger in this case, we'll say that we want to set n2 equal to n, which was equal to the temp, or temp, because this is the value that we set right here. This is how we flip the numbers. After that, we now know that n1 and n2 are going to be in the right order, so the n1 will always be bigger than n2. So, what we can now do is say, we can now call the GCD, and we can figure out what's the GCD of these two numbers. So we're going to create the integer GCD, and we're going to say that's equal to the method call GCD of n1, n2. Now what this says is, okay, we call the method GCD with n1 and n2. Then we assign the result, the integer result, and we know it's an integer because we can look at the method signature right here, and we assign that to the integer GCD, at which point we can divide by GCD on n and d. Now we had to initialize both n1 and n2 to 0, because otherwise, even though we know they're going to be given a value, Eclipse doesn't, and Java doesn't. So to be sure, we have to make sure that we assign them a stock value, even though they're never going to actually be equal to 0. We need that right here. So now that we have the GCD, we can actually figure out what's the reduced form going to be. So we're going to say integer reduced n for numerator is equal to n divided by GCD, and that's the variable GCD, and then the integer reduced d is equal to d divided by GCD. Now you might be saying, well, why can't we just call the method twice? You could, but since we're repeating the exact same value here, we might as well have a variable name for it. And we can use integer division here, because we know that we're dividing 2 by definition. When you divide a number by the greatest common divisor of another number, both of them will result in integer values. So there's no disadvantage to using integer division here. It's not like we have to cast 1 into a double. We'll still get the correct result. Now, we have the reduced form of the numerator and denominator. So we have to check, okay, is this going to be a whole number? So the way we check if it's going to be a whole number is to say, is the reduced n equal to the reduced d? Because in any number where it's a 1-to-1 for ratio of the numerator and denominator, that's what we want. So if it's, for example, 6/6, or 5/5, or 12/12, in all of those cases, in every case, the numerator is equal to the denominator. So we're going to have an if statement here that says if numerator, or reduced numerator, because the numerator might not be equal to it, but the reduced numerator is equal to the reduced denominator. And remember, we have to result in a Boolean value here, so we use our double equal signs. Then we say the string that we're going to be returning, remember the string reducer right here, which we can initialize right here to an empty string initially, but we'll add values to it obviously. Then we want to say that the reducer is equal to just the number. So we're going to say the reduced fraction is, and then we provide our number. So if the number is going to be 6/6 or 5/5, we can simply pick the numerator or denominator because it will result in the same value. So we say the reduced fraction is, and then we'll pick the numerator, and then we have the most reduced form. Now it's an interesting little quirk. Because we're reducing our fraction and we're returning them as whole numbers, whenever you do provide a value like 6/6, you'll actually end up with 1. And while this might seem like a problem, it's actually the right solution. Because anytime you have 6/6 or 5/5 or 3/3, the most reduced form of that is simply 1. So while some people find this confusing, this is the right implementation. If we have two numbers that are equal, the most reduced form is going to be the whole number version of 1. So instead of having the variable reduced n here, you can actually hard code in the value 1 because that's always going to be the result. We're not going to, but it's a choice you could implement. Now we have to check up at the other scenario. Now this is a one-line if statement, so we don't need our braces. But our other scenarios are going to be ones where they weren't perfectly reduced already. Now this will have to cover scenarios like 6/3 or 15/5, where it'll result in a whole value, but it's not going to be the perfect solution of 1. So to do this, we're going to have an else if statement. And this else if statement is going to say, well, else if reduced n modulo, because remember, modulo gives us our remainder, modulo denominator is equal to 0, then we know it's a evenly divisible fraction. But again, we have another way to cut down drastically on the time, because a Boolean statement like this actually takes a fairly significant amount of system resources. Instead, we know that if a fraction has been reduced to such a point where it ends up as a whole number, like 6 or 3, like 18/3, then we know that the denominator in that case will always be 1. 6/3 or 18/3 will reduce to 6/1. So we can say else if denominator, reduced denominator that is equal to 1, then we know that we have a whole number. So we can simply say that the reducer string, which we can copy paste from up here, is going to be the numerator. And this is because in such a scenario, the numerator will be the whole value. 3/1 is equal to 3. 5 over 1 is equal to 5, so we can simply provide in the numerator that we want. Finally, we have to have our else statement. This else statement will cover the non-clean cases. Remember, up till now, all the statements we've had have said, okay, if it's somewhat like this, or if it's like this, where it ends up as a whole number, either if that whole number happens to be 1, or if it happens to just be any old whole number, then we have those covered. We have to also cover the messy scenarios. These messy scenarios are the vast majority of cases with this program. So we have to say, well, else if it's 1/2, or 3/4, or 1/15. We have to cover all those scenarios too. Now, we've actually got all the legwork out of the way though, because we reduced our numbers right here. We can simply say reducer is equal to, and then we provide in our normal string, which we can copy paste from up here, that the reduced fraction is going to be equal to the reduced n plus the string of a slash mark plus the reduced denominator. Now you might be saying, well, what does all this mean? Because it looks fairly complicated. In fact, it's pretty simple. This covers every scenario where it's not going to be clean. So this is something like 1/15. It'll say, well, since we've already reduced the two numbers and we've stored those two reduced forms right here, we can simply just output that to the user or to the calling method. We'll say the reduced fraction is reduced n, which we have right here. Let's say that's 1 over the reduced denominator, and that's how we always output a fraction anyways. So now we have the fraction saying the reduced fraction is 1/15 or 3/15, where the over the denominator is going to be marked by a slash, and that's a normal slash, not a backslash. Now that we've covered all the proper scenarios, all we have to do now is simply return the appropriate value, which in this case is going to be the string reducer. And remember, this is why we didn't put 3 return statements in here. It's much easier to have an if, else if, and else that cuts in a simple string, and then we have one single return statement instead of 3 separate ones. It improves readability drastically, since now somebody doesn't have to keep tracing through their code. They can say, okay, all I have to do is follow the string reducer, and I know that's what's going to be output. So now that we've done this, we can now get the easy part, where in our main method, because remember, we have 3 methods now, the private GCD, the public reducer, and the public main method. Now, all we have to do is output this to the user. So we can say system.out.println, and then we're going to output the GCD call, or as we called it, the reducer. And we pass it the parameters of the numerator and denominator, which we marked off appropriately with the right names. This is why descriptive names are so helpful, because instead of having to guess what's n1, n2, we can simply just put these in. And now, what this is going to say is, okay, take the method reducer, pass it the parameters of numerator and denominator. Okay, those are, remember, these are called actual parameters. So it says extract the value from numerator, extract the value of denominator, assign the value of numerator to n, and the value of denominator to d. These are our formal parameters. Then use those formal parameters inside the method. First, make sure that they're in the right order, so switch them around if necessary. Then call the GCD method to get the GCD of the two numbers. Then we have to make sure we take those values, so we get the reduced numerator and the reduced denominator. Then we decide, okay, depending on the situation, we have our correct output, and then we just return that string. And our GCD method is the one we've created previously. So now, instead of having to have 6 different lines, or even 20 different lines, where we had to put in the reducer manually, and we had to put in the GCD method, we can simply call these methods, and we have a single line that does everything we need. If you think about how this works in the stack, because many people are intrigued by that, in the back end, it'll first load in the main method. It'll then run into this, and it'll say, okay, call the reducer method. Then it'll run through the reducer method and say, okay, we have to call the GCD method. Then it'll call the GCD method. So if you think about it at this point, it'll be the main method at the bottom, followed by the reducer method on top of that, and then the GCD method on top of that. Then once the GCD method finishes running, because it was the last in, it's going to be the first removed from the stack. So now it'll be left with the stack of just 2 methods, the reducer and the main method, with the reducer method being on top of the main method. And once the reducer method finishes running right here, it'll return its value to the main method, and it'll be removed from the stack so that you only have the main method. The main method will keep running so long as the user wants to keep the program running, because we created that right here. So now we can test out our program. So if we run our program, we have a lot of test cases here. A lot of these test cases are going to be somewhat overlapping. So our first test case is going to be a simple value. So let's try 3 over 3. So if we want to put in 3 over 3, we simply hit 3, enter. Remember, that's how we put in these values. The denominator will also be 3. And then you'll notice we get a value of 1. So if you want to check it now, you can either terminate the program by hitting -1 and the program stops, or if we want to try this again, we hit 3, 3, and then we put in another value. Let's say we put in 9. Now we can test out another scenario. This scenario is going to be, well, what if I have two values where one of the values is going to be bigger, but it's still going to come out to a whole number, like 6 over 3. So we're going to say 6, 3, and we get 2. So it works right there. And our final test case is going to be if it doesn't come out cleanly, so 2 over 15, and we get 2/15, and then we have to check for our case of it being even, or it being reducible but not even, so something like 21 over, let's say, 12. And you'll notice we get 7/4. So we know that our program works perfectly here. This is because if we go through our program, we remember that we called our methods, our method worked correctly, and we had all of these inside our reducer method. We made sure that we initially assigned it to n and d so that we gave a value, and then we had the appropriate method calls and reduced and returned the appropriate values. Hopefully you enjoyed this little case study. It was a fairly lengthy and powerful case study. To summarize, in this lesson, we built a program that could take input from the user, keep running as long as they wanted to, reduce the number. If it was a whole number, returned as such. If it was a clean number that would go 3 over 3 or 6 over 6, it would return 1. Otherwise, it would reduce it down to its lowest form. And if there was no reducing, it would simply reduce it or return it as is. Hopefully you enjoyed this lesson, and hopefully you were able to practice all of the ideas we've talked about with methods so far.